Nearly 4,000 people in the US are waiting for heart transplants, and on average it takes about 6 months to get one, during which time some patients will die. So researchers have been trying for decades to make an artificial heart that can be permanently implanted, but building one that imitates a real heart over a long period of time without breaking or causing infections or blood clots is incredibly difficult. Want to know about it? Well, stay tuned to the video and watch the video till the end. Hello guys, welcome to Futureality. Hit the subscribe button and turn on the notifications to get new updates about technology and development. Hit the like button to show your support, and in today's video we're going to discuss, could a robotic heart save humans in the future? So without any further ado, let's begin. Heart failure affects over 10 million people in the US and Europe every year, and the outlook for patients is often bleak. Medication can only control the condition for so long, and most patients require a complete heart transplant. If your heart slowly failing isn't scary enough, the number of donors' hearts that become available each year is tiny compared to the number of people waiting for one. For some patients, their size or blood type means the chances of finding a donor's heart are virtually zero. Attempts have been made to design artificial hearts since the 1950s with little success. Artificial hearts aren't new, and neither is using cow parts in transplants, yet the latest innovation by a French biotech firm, Carmat, has proven that using both machine and cow parts to build a healthy heart can actually work. The artificial heart has been around for decades with varied success. Constructing a machine that can withstand the human circulatory system and can pump 35 million times a year is quite difficult. This man-made heart will hopefully act as a long-term replacement for patients waiting to get a heart transplant, improving their quality of life while in transition. Known as a bioprosthetic, it's comprised of two chambers encased in the same sac that encloses a cow's heart. The valves that make up the heart are also taken from the cow to help adjust the rate of blood flow. Since the heart is made up of biological components, it's less likely that patients using the heart transplant will become dependent on anticoagulation medication. The idea was to develop an artificial heart in which the moving parts that are in contact with blood are made of tissue that is better suited for the biological environment. Pia Jansen, Chief Medical Officer of Carmat, told MIT Technology Review, approximately 32,500 persons aged 55 to 70 years with end-stage heart disease may be potential candidates for the artificial heart each year. However, continued application of a protocol that requires informed consent by the patient effectively limits the pool to 12,000 annually. Estimates of the cost of the artificial heart include charges for the surgical procedure, device and console, and continuing medical surveillance. These estimates range from a low of $100,000 to a high of $300,000 per patient in the initial year. Assuming a 5-year 51% survival and an initial cost of $100,000, total program costs in the 5th year are projected to be $1.3 billion for a pool of 12,000 patients and $3.8 billion for 32,500 patients. More than 1.3 million patients with diseased heart valves need valve replacement globally each year. There are two types of artificial valves currently available, however, both have limitations either in durability or in biocompatibility. Biological valves are made from pig or cow tissue and have good biocompatibility, meaning patients don't need lifelong blood-thinning medication, however, they only last 10 to 12 years before failing. And mechanical valves, while they have good durability, have poor biocompatibility, and patients must take daily blood-thinning drugs to prevent blood clots. Professor Jeff Mogridge from the University of Cambridge and Professor Raimondo Ascione from the University of Bristol have spent 3 years conducting developmental work and testing on the polyvalve, supported by funding from the British Heart Foundation. The device is made from a special copolymer and is designed to resemble a natural heart valve. It was created by Professor Mogridge, Dr. Marta Serrani, and Dr. Joanna Stasiak at Cambridge and Professor Ascione in Bristol, and builds on earlier work by Professor Maria Laura Costantino's group at the University of Milan. The polyvalve combines excellent durability with biocompatibility, addressing the limitations of current biological and mechanical artificial valves. It's made through a simple molding process, which also sharply reduces manufacturing and quality control costs. These impressive results show the polyvalve is a promising alternative for valve replacement surgery, said Mogridge, who leads the structural materials group at Cambridge's Department of Chemical Engineering and Biotechnology. While further testing is needed, we think it could make a major difference to the hundreds of thousands of patients who get valve replacement surgery every year. The complex system of artificial pumps and valves required to beat over 100,000 times a day and tens of millions of times a year get worn out, meaning mechanical hearts can start to fail even more rapidly than the diseased hearts they replace. The few artificial hearts that have been approved for human use are currently only ever used as a last resort to buy a patient time before a real transplant. Patients have to wear cumbersome power boxes at all times, and wiring runs in and out of their chests, leading to infections. But a completely new design known as Bivacor could revolutionize the use of artificial hearts and the way heart failure is treated. Instead of trying to replicate the way a real heart pumps, the device uses a single spinning disc to drive blood to the lungs and body. With a high-tech rotary pump levitating between magnets, there is virtually zero mechanical wear. The lack of other moving parts means the rest of the heart can be made from ultra-robust titanium, as well as its state-of-the-art levitating disc technology. The Bivacor heart can adapt its output to the physiological demands of the patient, so it'll pump faster during exercise, and can be made small enough to fit into a child. It's also hoped that the device can one day be combined with wireless charging technology, meaning that the battery could also be implanted into the patient instead of carried externally. A viable artificial heart would greatly alter current treatment for end-stage cardiac disease. More patients would benefit from this therapy than currently benefit from heart transplants, and the costs of caring for these patients would increase substantially. The current state of development of the artificial heart provides an opportunity to collect data on investigational artificial heart performance, clinical results, patient status, and economic social costs. This knowledge base would be invaluable for future technology assessments and policy decisions regarding third-party reimbursements. According to ISO standards, a new artificial heart valve must withstand a minimum of 200 million repetitions of opening and closing during laboratory testing, equivalent to 5 years of lifespan, before it can be tested in humans. The new Cambridge-Bristol polymeric valve has comfortably surpassed this. Initial testing in sheep has been undertaken at Bristol's Translational Biomedical Research Centre (TBRC) facility as a first step to ensure safety. Long-term testing in sheep, also funded by the British Heart Foundation, will be carried out before bringing this new treatment to human patients. Patients requiring an artificial heart valve are often faced with the dilemma of choosing between a metallic or tissue valve replacement, said Professor Sir Nilesh Samani, medical director at the British Heart Foundation. A metallic valve is long-lasting but requires the patient to take lifelong blood-thinning drugs. Although this medication prevents clots forming on the valve, it also increases the risk of serious bleeding. Patients who have a tissue valve replacement usually don't need to take this medication. However, the valve is less durable, which means the patient may face further surgery. The polymer valve combines the benefits of both. It's durable and would not require the need for blood-thinning drugs. While further testing is needed before this valve can be used in patients, this is a promising development, and the BHF is pleased to have supported this research. Long-term, it's hoped that Bivacor hearts can replace the total function of the patient's hearts and offer hope to millions of people who are waiting or unsuitable for heart transplants. Now that we've come to the end of this video, I want to thank you for sticking with me, and I'd love to know what you think of it. Just comment down below. Also, if you like this video, make sure you like it and stay safe. Today's video is over, but if you want to see more, there's one on your screen right now, and there are a few more fun videos coming soon. I'll see you in the next video.